So in our last video, we talked about how our work and energy look a little bit different when we're dealing with our rigid body instead of dealing with a particle. And with that, we said that, okay, for work, now we have to take into account that a moment can do work. That's really one of our new things. And then the other thing to take into account is that our kinetic energy equation is just a little bit different. Right, so we said if our moment does work, then that's going to be our moment times whatever angle theta that displacement is caused. And we said our general form for our kinetic energy is now not only going to be the 1/2 mv squared, but we're also going to add on to that 1/2 ig omega squared, where ig is your moment of inertia and omega is your angular velocity. So with all of this in mind, we're going to do exactly what we did with our particle kinematics, right? Particle kinetics, when we talked about work and energy. And in that, we had this principle of work and energy, where T1 plus summation of forces that do work, a summation of our work from location 1 to location 2, equals our kinetic energy final, that kinetic energy in the final position. And this equation is exactly the same, right? This is the exact same principle of work and energy that we use for particles that we're going to use for rigid bodies. Just know that we do have those rotational velocities and rotational moments that contribute to the work and to the kinetic energy that have to be included when we're solving these problems for our translation, our rotation about a fixed axis, and our general plane motion. Right, so if we recall from when we talked about our particle kinetics, we said that we typically use this when we're given forces, velocities, and displacements. So a lot of times you'll be finding a force, maybe you'll be finding an angular velocity, omega. Maybe you're finding a displacement that is in the theta direction, right? An angular displacement. So you could be finding any of these things, best used with our principle of work and energy. So we're going to do essentially the same process that we've kind of done with our equations of motion, where we're going to draw our free body diagrams, and then we're going to draw a kinematic diagram where we kind of write out what velocities and displacements that we have in our initial or final conditions, so that we can work out what these kinetic energies are, what the works are, and plug those all in so that we can find whatever it is that we're looking for. Right, so it's going to be very similar to what we did for particles, just now applied for rigid bodies. Make sure that we're taking into account those rotational moments, rotational, are those angular velocities, I should say, and solving problems with those. So with that being said, let's go ahead and take a look at a couple of examples. All right, so for in our first example here, we have an 80 kilogram wheel that has a radius of gyration about its center of mass O of k equals 400 millimeters. And we want to determine its angular velocity after it's rotated 20 revolutions starting from rest. So we can see if we look at our little diagram here, we have this wheel that's pinned in the center. It's pinned at O there. That wheel has a radius of 0.6 meters. And then we have this force P that's leading from the top, right, kind of tangential to the top of that wheel there, with a force of 50 newtons. So if we kind of imagine in our minds like how this thing is moving and what's happening, first kind of classifying it of what kind of motion is this, right? So since it's pinned in that center there, all we do is we have the wheel that is just rotating about its center, right? It can't actually translate, it can't move at all. It can only rotate about the center O, so this is a rotation about a fixed axis problem. And so we know that we've got a rotation about a fixed axis, and that rotation is being caused by that P, that force P that is pulling on the top of that wheel there. So kind of understanding what we've got there, we have it starting from rest, and then it's going to rotate through 20 revolutions, and we want to find out what that angular velocity is after going through those 20 revolutions. So that's what we have going on kind of physically. Now we're going to take that physical concept and we're going to bring those into our diagrams. And so we're going to draw a free body diagram and a kinematic diagram. So our free body diagram we should be pretty comfortable with, right? Those are just showing all of our forces on this guy. So our free body diagram for the wheel, you're of course going to have the force P that's coming off of the top there, that 50 newtons. And then don't forget that because it's pinned there in the center at O, there are forces there, right? There are reaction forces at the pin, OY and OX. But other than that, that's it. It's pinned into the wall. It's not on the ground or anything. There's no normal force to account of, or to account for, I should say. So those are all of the forces that we have in this free body diagram here. Then we're going to come to the kinematic diagram, and this is just a little bit different than the kinetic diagram we had been using with our F equals ma equations, right? Those equations of motion. So with those kinetic diagrams, we were drawing the mass times acceleration vectors. But here we don't really care about acceleration. We really only care about our displacements and our velocities. So that's what we're drawing in these kinematic diagrams. So in the kinematic just a little bit different from our kinetic diagram. The kinematic diagram is showing that rotation. It's showing what the movement is going through. Where initially, since you have this wheel at rest, there's nothing happening. There's no velocity, no displacement has been gone through yet. There's nothing to put on here. No motion has occurred. But then your final setup, so number 2, your final setup would show that, hey, this thing now has an angular velocity. It has an omega. And it goes through 20 revolutions, right? It has gone through 20 revolutions. 20 revolutions. So remember, one revolution is one full time around the circle, so it's gone through 20 of those. You don't need that on your diagram. I would just make a note of it that it's gone through the 20 revolutions. And then it will have some angular velocity, right? So your theta that it travels through, 20 revolutions, which we need to convert into radians, but we can do that in just a second. Your kinematic diagram is kind of capturing those velocities, angular velocities, displacements, any of those, so we can understand our kinetic energy a little bit better. Because now our free body diagram is really where we're going to be pulling the work from. And our kinematic diagram is really where we're going to be pulling our kinetic energies from. So let's look at that. Let's go ahead and look at our formula and see what we can bring out of these guys. So T1 plus summation of my work 1 to 2 equals T2. So let's look at each individual part of this before we put this together in this equation. So T1 is going to be 0, right? We're starting at rest, which means that our T1 for our 1/2 mv squared plus 1/2 I-O, since we're rotating about our center of mass O there, I-O times omega squared. Since our initial velocity is 0, there's no initial velocity. Initial angular velocity is 0, there's no angular velocity starting from rest. It's just 0. Right? Easy as that. Then we'll go ahead and look at our work. I'm just realizing my free body diagram is missing a force. I need to add that on here. My weight is a force. Thought I captured everything at O, but I didn't. There's a weight force at O. This drum has a weight. This wheel has a weight of 80 kilograms times 9.81. Whoops. Sorry. It's going to be important because we're going to do our work calculation and we need to know all of the forces that are doing work. When we look at this sum of U1 to 2. Right, so any movement that's occurring, any displacement that is doing work, we need to account for. So looking at our now actually complete free body diagram, I want to pull out the forces that are doing work. So I know that my OX and OY aren't going to be doing any work, right? That point O isn't moving at all. It's just those reaction forces that keep it there in place. And we'll also notice that the weight actually isn't doing any work at all there either, because again, that center of mass is not moving. If this wheel were falling through the sky while pinned to those axes, then maybe that work would be, or that weight would be doing work. But in this case, our weight isn't actually doing any work. There's no displacement there in the y direction, so weight is not doing any work. And the only force that does work in this free body diagram is the work done by P, right? P is what's causing those 20 revolutions, those rotations about that fixed axis. P is the only thing that's causing that. So we only have work done by P force. And of course, since that P is a constant force, it's just going to be the force P times that displacement S. Right? F times S. And so if we recall, our S value is going to be that displacement around the circle there, right? This displacement that the wheel is experiencing is the entire round of the circle for 20 revolutions, over and over and over and over again. So our displacement S equals theta times R times the number of revolutions that we're going through. Right, so in this case, we're going to have our S value is theta. Theta for one single revolution is 2 pi. Right, that's the full circle. One revolution is 2 pi. And then we do that 20 times. Right? 2 pi for one revolution times 20 revolutions times our radius of 0.6 meters. And then we can take that and plug that in, multiply by our p-value, since that p-value is constant, to get what our work is. Oops. I'll call this UP, the work done by force P. So when I plug this in, I get that the work done from force P is 3,770. And let's see, I had this in meters. This is in joules or Newton meters, whichever you like. And since that's my only form of work, that is going to be the summation of all my works. That's the only force in my free body diagram up here that does any work. So we have our initial kinetic energy, we have the work done to it, and that's going to give us our final kinetic energy. So looking at that kinematic diagram, we'll notice that there is no actual velocity. There's no like linear velocity here. We only have an angular velocity, right? The whole shape isn't moving. There's no velocity to the wheel itself, only an angular velocity from the rotations there. So that's going to give us T2, 1/2 mv squared plus 1/2 IO omega squared. And we just said that since it's not moving, right, since it's pinned there, it's just rotating about a fixed axis, there's no linear velocity. We're only going to have that 1/2 IO omega squared. So 1/2 times IO. What's our IO? Right, that's our moment of inertia. Moment of inertia about point O. And they gave us a K value, right? They gave us that radius of gyration. So we can use IO is MKO squared. So the mass is 80 kilograms. The K value was 0.4 meters squared, which gives us an IO of 80 times 0.4 squared gives us 12.8 kilogram meters squared. And so we can plug that in down here, 12.8 times omega squared, right? We don't know what omega squared is. We don't know what that angular velocity is. We're trying to solve for that. And now we can bring this all together, right? We can come back to our equation up here, bring everybody together and solve for that omega. We're going to have 0 plus the work, which was 3,770, equals 1/2 times 12.8 times omega squared. Right, just very basic, not any other equations that we need to solve for. We can just set up the one single equation here and get that our omega is 24.3 radians per second. 24.3 radians per second. And I'm going to use a positive answer for that. Whoops. And assume it is moving in that clockwise direction there, in that same direction as P. Assuming that it causes that rotational force there. Or not rotational force, just that rotational movement, that clockwise movement for omega. Right, so this is a little bit simpler. These work and energy, principle of work and energy, the reason that we like to use them is because they can save us from having to plug in multiple different equations to find one thing. Right, so when we're dealing with forces or velocities, angular velocity, displacements, this can give us kind of a single step equation, like one single equation to use, instead of having to use multiple equations plugged into each other. So that's why we kind of talk about all of these different forms that you can use, whether you use the F equals ma, or the work and energy that we're talking about now, or as we're going to talk about, in our next few videos after these, the impulse and momentum. Right? They all have these kind of different use cases that can save you some time and make the approach to the problem a little bit easier, just depending on what you're given. And so that's why we look at all of these different use cases, right? Just to save you time, just to make things a little bit easier, even if it doesn't seem easier now while you're kind of learning all this new information. But with all that being said, let's go ahead and take a look at another problem. And this time we'll look at some general plane motion problems to see how those work a little bit differently than our rotation about a fixed axis. So for this example, we have a rod that's leaning up against a wall, and it tells us that the uniform 50 kilogram slender rod is at rest in the position shown when P equals 600 newtons is applied. Determine the angular velocity of the rod when the rod reaches the vertical position. Right, so we've got this rod AB, it's leaning up against a wall, making a little 3-4-5 triangle with the wall, since that rod is 5 feet long. And then it tells us that we're going to be moving from this position, where we're initially at rest, and moving up to the wall, right, making it into the vertical position. So what might be helpful is not drawing just one free body diagram or one kinetic diagram, but it can be really helpful to draw them for the initial condition and the final condition, instead of just a general condition. So I'm going to go ahead and draw all of those, right? Our initial and our final for each of these, so we can kind of look at what's going on here. So for our free body diagrams, initially, this one, we have this rod. Whoops. Draw that a little more angular there. So we have our rod. We know that this rod has a mass, and that mass is going to act in the center of that rod. And we're just going to assume it's a uniformly dense rod, so halfway through the rod there, acting straight downwards. I could draw straight lines a little better. Straight downwards, we have the weight of the rod. They also tell us we have that applied force P going directly to the left at B there, where P is 600 newtons. And then looking at any other forces we might have here, the only other ones that we have are the normal forces where this rod is touching the wall. Right, so there's a normal force from the floor at B, and there is a normal force from the wall at A. So this is our initial condition. This is what we're starting with. And maybe we'll go ahead and do our initial condition for our kinematic diagram too. Right? It'll be pretty straightforward for our kinematic diagram. So 1, we initially have that bar. And they told us that this slender rod is at rest. So there's actually nothing to put on our initial kinematic diagram here. We know initial angular velocity is going to be 0. The velocity is 0. There's no displacement, so we'll say that initial like angle that we're at. We have an initial angle that we're at. We can like determine that if we want to, but it hasn't gone through any displacement yet. Right? So no movement, just sitting at rest. Omega 0, v is 0. Then I'm going to come through and let's do our free body diagram for the final position. Right, so in the final position, we still have all of these forces still applied, but now our rod is vertical. I'm having trouble drawing straight lines today. Oh my goodness. There we go. All right, so we've got this straight vertical rod. For now, we'll notice, our weight still acts in the center there, but that weight is now in line with the rod. Right? The way that the rod has rotated and moved into that vertical position, the direction of the weight hasn't changed, but the way that it interacts with the rod has. We still have the normal force at B. We still have E force at B, still have that normal force at A. And so all of that stays the same. All that's really changed is kind of how the geometry of the problem was. Because initially we had, this 5 meter rod here that had this vertical height of 4 meters, and then because this makes the 3, 4, 5 triangle, this is 3 meters away. But now we can see in our position 2, the vertical height is the same as the rod height. They're both 5 meters. So what that means is like where this weight is acting is a little bit different. Initially, our weight is acting halfway through this 4 meters, right? Now it's acting at a little bit different of a position. Instead of acting at this 2 meter mark, acting at this 2.5 meter mark. It's moved, right? Where the center of mass is has moved from where it was before. And A and B have also moved, right? Those positions, all of the positions of those points have moved because this is a general plane motion problem. So now we'll go ahead and take a look at our kinematic diagram and see if that's any different now that we've swung into this vertical position. And so at 2 here, we can see that not only has it kind of swung around, but if we use A as a base point here, we've gone through this angular velocity around A, and this center of mass has a velocity as well, as it's coming up, like the second that it's bumping up into that vertical. Right as it's about to hit the wall there, the second that beam becomes vertical, or this slender rod becomes vertical. Our velocity for the center of mass acts at the center of mass and is going directly to the left, right? It's going in the direction of that angular velocity sweep, in the direction kind of of our force as well. And so if we want to, using this A as a base point, we can also go ahead and come in here and say, all right, I have this R vector, R of G with respect to A, showing the kinematics of that, right? How do position relate to our angular velocity and our radius, right? How do these vectors work together? VG, omega, and R. So R is the thing that unites those VG and omega vectors. If we recall, our VG is going to be omega RG with respect to A. So for our case, VG is 2.5, right? Because that distance, since that rod is 5 meters, the halfway point there is 2.5. So Vg is 2.5 times omega. So that kinematic diagram gave us this relationship. Right? Remembering back a couple weeks ago when we were doing all of these kinematic diagrams, solving for velocities, relating those velocities to our angular velocities and our position vectors, that's where this is coming from. All right, so with all of that in mind, since we're finding an angular velocity and we're given a force, we're going to go ahead and use our work and energy, our principle of work and energy, right? That work and energy equation. T1 plus sum of all the work done equals T2. All right, so let's start with T1. Looking at my first kinematic diagram, right, my T1 is the 1/2 mv squared plus 1/2 ig omega squared. And since I'm starting from rest, I guess I can write all these out. 1/2 mv squared plus 1/2 ig omega squared. As I'm starting from rest, there is no initial velocity and no initial angular velocity. So that makes it easy. Once again, that kinetic energy initial is just 0. Then I'll look at what's doing work. So my work is going to come from my free body diagram, and remember that our work is only force that causes displacement, right? Only forces that cause displacement get counted as work. So typically this means that our normal forces almost never do work. And if we look at our NA and our NB, we see that neither of those cause a displacement, right? Neither of those forces cause displacement, so neither of them are doing work. So not anything from NA, not anything from NB. And then we can see, we have that applied P force. We have that 600 Newton force at P. That most certainly is doing work, right? That is definitely doing work. So from P, we have the constant force P times the displacement that it does, which is S. So as we can see that S, we're moving from B to a vertical position here at the wall. And we said this was a 3, 4, 5 triangle, so this distance that it's moving through is 3 meters. So for P times S, that's going to be 600 newtons times 3 meters is 1800 Newton meters or 1800 joules, whichever you like. And so that's one of them. That's our work from force P. And then what other forces haven't we looked at yet? We've got just the weight. Just the weight from our free body diagram here. So looking at our weight, when we have this guy initially, let me bring this up a little bit. When we have this guy initially, our center of mass is right here. So again, that center of mass is occurring 2 meters up from the ground. This distance here is 2 meters. But then as this shifts in towards the wall, now this guy A is moved up a little bit, B is still on the ground, and what we see is that now the weight center of mass is up here. It's still halfway through that 5 meters, but that 5 meters is entirely along the wall. So now instead of being at 2, it's higher. It's up at 2.5 meters. So that weight is doing work, but it's actually doing a negative work, right? Because our weight is pointing downwards, but our object has moved up. So even though it's doing negative work, it still has to get counted in this, where we're going to have our work from weight is weight times delta y. So the weight was, what's our mass of this rod? 50 kilograms. 50 times 9.81 times our delta y. Again, we went from 2 to 2.5. So from 2 to 2.5 is going to give us a negative delta y. So that gives us negative 245.25 Newton meters. And that was it. Those are all of the forces in those free body diagrams. Normals don't do work. We got weight, we got P. So our total work, U1 to 2, is going to be 1800 minus 245.25. And then finally, we'll go ahead and take a look at those kinetic energies. Right, T2, final kinetic energy. Recall T2 is going to be 1/2 mv squared plus 1/2 Ig omega squared. So from our kinetic diagram, we do have a Vg, we have a velocity, we have an angular velocity, and we already decided what that relationship was going to be between them. That Vg equals 2.5 omega, just based on the kinematic diagram, just based on those relationships there. So since we're trying to find our angular velocity, I want to see if I can put everything in terms of omega. We're going to have 1/2. The mass of the rod we said was 50. Yes, mass of our rod was 50. Vg, instead I'm going to put this in terms of omega, so 2.5 omega squared plus 1/2 times Ig. And if we think about our Ig, look at our problem statement, we don't have a radius of gyration, so we can't use that shortcut. But it does tell us that the shape is a slender rod. And we can go look up in our tables or in the back of our textbook what the Ig, like general form for a moment of inertia of a slender rod is. And from our textbook, Ig for a slender rod is 1/12 ml squared. Right, and that's about G, that's about its center of mass there, not about any one end. So Ig is 1/12 ml squared. I can plug that in down here. 1/12 times the mass of 50 times the rod length of 5 meters. So that is all Ig. And then we multiply that by omega squared. And with all of that now, our only unknown is that omega. So we can go ahead and plug all of those in. And we get 0 plus 1800 minus 245.5 equals, and then I can, multiply this guy out some, 25.2 times 2.5 times omega squared plus, I simplify? Oh, I did. If I punch all of this into a calculator, I get 52.1 times omega squared. Then I can simplify that to solve for omega. And I get our angular velocity is 2.73 radians per second. So that's our final angular velocity when that rod reaches the vertical position. And if we wanted to, I could come back up and calculate what the actual velocity is. That linear velocity is Vg. Vg is 2.5 times omega. That would be 6.83 meters per second. Just if we were looking for one or the other or both, we could do both. So this is an example where we have to account for the fact that our kinetic energy has both of those components, right? With the general plane motion, it has a V and an omega. Velocity and angular velocity, both of those have to be captured in the kinetic energy. Go ahead and take a look at one more example. All right, so for our last problem, we're back to another wheel example, but we'll notice that this time we're not rotating around a fixed axis, we're rolling along the ground here. Okay, so we're attached to a spring, and then we have this wheel shown that weighs 40 pounds and has a radius of gyration of k equals 0.6 feet about its center of mass g. It's subjected to a clockwise moment of 15 pound-feet and rolls from rest without slipping. Determine the angular velocity after its center g moves 0.5 feet. Spring has a stiffness of k equals 10 pound per foot. K equals 10 pounds per foot, and is initially unstretched. Right, so they give you a lot of information here, both in the words and in the picture. Right, so they show you that the spring there is attached to the top of this little wheel at A, and that moment is being applied around G, forcing it to turn to the right. Right? So again, it's not rotating about G, but it is moving along the road, right? It's rolling without slipping, as it says. So with this in mind, let's draw our diagrams. Start with my free body diagram, as always. And with this, I'm just making it about the wheel, right? The spring is contributing a force. My free body diagram is really just capturing the forces that are interacting with this wheel. So I have my free body diagram here. I'm of course going to have the force from the spring attached at the top A there. Call this Fs for the force of the spring. It tells us that the wheel shown has a weight of 40 pounds and that's acting at G. So at G, I have a weight equals 40 pounds. And then looking at this, let me look through my prompt. Do I have any other, let's see, weight of 40 pounds, radius of gyration K, that doesn't apply to my free body diagram. Subjected to a clockwise moment. Yes, our clockwise moment, right? We haven't had a lot of moments yet in our free body diagrams, but it's very important that we include them, right? They do go on a free body diagram. So I'm going to pop this guy right in here, an applied moment of 15 pound-feet. Rolls from rest without slipping. So that rolls from rest without slipping is really important, really gives us some good information that there's probably not a frictional force in here, right? There's no friction indicated. And we want to determine its angular velocity. Spring, we've got our spring. And so looking at this, really the only other force that we don't have in this free body diagram yet is the normal force from the ground. Where it's touching the ground there, got a normal force. So that pretty much captures all of the forces and moments that we need in our free body diagram. And then we can come over here and draw our kinematic diagram, right, showing how this thing is moving. We want to determine that angular velocity after the center moves 0.5 feet. Right, so initially my center G is here, and now we're saying, all right, same wheel on the ground here. Center G is now here. We have moved 0.5 feet. So this is what we're trying to figure out. What is the angular velocity when we're in that position? Move that so that way I can keep this a little less messy. Got my wheel. Since this is rolling without slipping, we know in our minds, we know a few rules for that, right? We say, okay, I know if something is rolling without slipping, I know that my center moves with a velocity of VG and is moving perfectly horizontal. Of course, we know that there is an angular velocity associated with it. We need to find what that angular velocity is. Some other relationships that we might think of when we're trying to think back to our rolling without slipping problems is that we know that we have a spot that is our instantaneous center of zero velocity. And when we're rolling without slipping, the instantaneous center of zero velocity is at the very bottom of our shape. Where that wheel is rolling and touching the ground, we have that instantaneous center of zero velocity, IC. Do we need it? I don't know. We might use it for this problem. It's just one of those things that we can kind of remember. One of those things that we can use and remember. So with all of that in mind, Let's go ahead and set up that principle of work and energy. Let's see, what color do I want? Pink. T1 plus sum of U1 to 2 equals T2. So for our T1, lucky us, in every single example here, it seemed like we all started from rest. So starting from rest, that makes it easy. T1 is just 0. Then we'll go ahead and look at all of our forces that could do work here. Remember, we have 4 different components on that free body diagram, and remembering that our moments can do work. So looking at what we have here, our displacement is going to be just to the right. That displacement is, again, maybe I should leave it on here, just 0.5 feet to the right. Only in the x direction, which means any forces in the y direction aren't going to do any work. So W doesn't do any work. The normal force doesn't do any work. But our spring force and our moment are both going to do work. So we need to find work of the spring force and the work of that moment. So let's start with our moment. That's our new one. Where we said the work of a moment, if the moment is a constant moment, we can do the moment times delta theta. And if it's not a constant moment, we could also do the integration form from theta 1 to theta 2 of m d theta. We could use either one of those. But since this moment is constant, it's not changing with theta, it's just a constant applied 15 pound-feet. We can plug that in. Right, so the moment is 15 pound-feet. And then we have to figure out, all right, well, what is this theta that we're rotating through? What is this angle? This angle in radians that we're rotating through that this moment is causing. Okay, so this guy is moving half a foot to the right. So if we write this out, right, we have this guy, then he moves over here by half a foot, where the point that we had here is rotating down along this way in the direction of the moment. So now we end up somewhere maybe over here. And so how can we relate those points? And so what we can do is we can say, okay, well, our S is theta times R. We know our arc length equation. Our S is theta times R. And so this displacement that we're going through from point to point here is going to be our S. So theta equals S over R, where S is 0.5, and we know the radius of that wheel was given as 0.8. And so we can find the angle that it rotates through is 0.625 radians. We can plug that in over here to our theta. So that's our 15 times our change in theta, 0.625. We get the work from the moment is 9.375 pound-feet. Perfect. So we've got our work from our moment. We need our work from our spring. If we remember that equation, that's going to be negative for the whole thing. The whole thing's negative. 1/2 ks2 squared minus 1/2 ks1 squared. Let's take a look. Now, when we read through this problem, you might have noticed, geez, we have 2 different k values here. And this is going to happen to you a lot in engineering school. We use k values for a lot of different constants. And so usually you'll just have to keep them straight by name alone and understanding where those get applied. right? So our spring, our coefficient of a spring, right? The spring stiffness constant is a K value, but our radius of gyration is also a K value, and they mean wildly different things and they get applied wildly differently. They have different units, but they do use the same symbol. They share the same letter. So just know you want to use for your spring stiffness, make sure you grab that 10 pounds per foot. So my spring, work of my spring is going to be negative 1/2 times the spring constant of 10 that we just said, times S2. And remember, S2 is the distance that you stretched from the unstretched length. So let's see. So if we've moved out by 0.5 feet, then we've got to think, you know, how much has this spring actually stretched? Our spring was initially unstretched, so that's perfect. We can have our initial position just be 0 for that displacement there. But how far did that spring stretch? Did it stretch out just by that 0.5 feet? Not really, right? That cable has kind of wrapped around the wheel here. This cable that's attached up here at A has kind of wrapped around as this thing goes around and caused more stretching in the spring than just the 0.5 feet that it's undergoing. Right? It takes into account the fact that we've gone through an angle here. We've gone through that 0.625 radians. So this is actually a case where our IC could come in kind of handy. So if I look at where my bottom is here, and I want to find out how far has point A moved. How far has point A moved? SA equals theta times R A with respect to IC. Or how far has my point A moved as we go through this angle? I don't know that it goes all the way down to IC. I think it only goes maybe about here. Right, that angle theta that we said was 0.625. So my displacement of point A is going to be 0.625 times the full diameter of the wheel, 1.6. So the displacement that the spring actually goes through is 0.625 times 1.6 is 1. It's 1. Right, so that just keep in mind that displacement is a little bit different. It's not the exact same as the displacement of G. The displacement of point A, where K is attached, is different than the displacement of G. And so with that, we get that the work from our spring, and it's initially unstretched, so that's -0. This all equals -5. -5 pound-feet. Okay, so we have that. We have our initial kinetic energy. Now we just need that final kinetic energy. T2 is 1/2 mv squared plus 1/2 Ig omega squared. But if we recall, we talked about in our last video that we have another kinetic energy formula. We could also use for rolling without slipping, instead of using this, we could use 1/2 times moment of inertia of IC times omega squared. So that IC, because this is rolling without slipping, we can find what that IC is. Right? It helps us cut out the middleman of finding out what VG is. Just if we wanted to, just to show you a little bit of a different way to solve this. So IIC is going to be IG plus MD squared. So IG is MK squared. Then we're going to do plus MD squared, where D is the distance between our G and IC. The distance between G and IC. So my moment of inertia IC is going to be, my mass is the 40-pound wheel. So 40 pounds is the weight. We want to divide that by 32.2. Times the K value. They gave us that radius of gyration here, 0.6 feet. Square that. Plus the mass again, 40 over 32.2. Times the distance between G and IC. So G is at the center, IC is at the bottom, so that distance is just the radius of 0.8. 0.8 squared. And that gives me a value of 1.24 slug feet squared. So for T2, I can write 1/2 1.24 times omega squared, and then finally plugging all of these in to our principle of work and energy. We're going to have 0 plus 9.375 minus 5 equals 1/2 times 1.24 times omega squared. And doing the algebra for that calculation gives us an omega of 2.65 radians per second. Right, so several different ways you can do these problems, a few different ways that you can approach them, whether you're using your IG or your IIC, your different moments of inertia, you can use different approaches for your kinetic energy. Just making sure that you're capturing the work, understanding kind of the geometry of the situation and how those displacements are interacting. Those displacements are really the key to getting that work correct. If you can get those correct displacements, you can get the work, and then you can get your kinetic energy with, either the general form or a more specific form, like we use the IC form in this case. And from there, it's usually just a very simple algebra kind of plug and chug situation. So in our next video, we're going to go ahead and look at conservation of energy and how that works just a little bit differently in our rigid bodies than it does for our particles. And we'll take a look at that next time.